Hello.
Hello.
So we'll begin in 2 minutes. I hope I'm audible. हेलो मेरा एक क्लास है बाद में बात करते हैं। क्लास है मेरा बाद में बात करते हैं। So I hope I am audible. So we'll start now. So welcome everyone. Okay, so by mistake I have written week 7 and today is week 8. So this is the last week of this uh, program or this course, which is strategy and introduction to game theory. And I am one of the TA for this course. I am Shubham Keshri. I am a PhD student in the Department of Management Sciences at IIT Kanpur. So in today's lecture, we will cover the concepts which is taught in this week's lectures, and the flow of the lecture, the flow of this session will be such that we will discuss problems, and through those problems we'll understand some concepts. If you have any doubt, you can just unmute yourself and speak. You will not be able to find the option of chat at your end, so please speak up. Okay. So we'll start from a very basic game, the Ultimatum game. We have done this game previously, but the concepts which we will discuss this week requires the idea of this game. Okay, so this game over here is a one-stage game. So in this Ultimatum game, we have two players, player 1 and player 2, and this is a discrete version of this game. Okay, so they have 12 biscuits and they want to divide this biscuit between themselves. So the game proceeds this way. First, player 1 proposes and offers some biscuits to player 2. Player 2 can either accept the offer or reject. If player 2 accepts the offer, the biscuits are split according to the proposal, and if player 2 rejects, then they get nothing. Alright? So the idea is to find the subgame perfect Nash equilibrium of this game, and it is given that the biscuits are indivisible. So you cannot have 11.5 biscuits or 1.5 biscuits. You can just have integer number of biscuits. You can take a minute, you can try, and then we'll discuss how to solve this problem. I'll just draw the table, not table, game tree for you. This is the node at which the game begins, and player 1 acts over here. Player 1 has multiple actions, and when at any node a player has multiple action, we denote it by this, indicating there are multiple actions in this uh, at this node. So he can either start giving 0 and it goes till 12. So there are many numbers in between these two strategies. It can be 0, 1, 2, 3 till 12. All right. Suppose it is x. Now at this node, player 2 acts. So x is the number of cookies or biscuits in this case, which player 1 offers to player 2, and player 2 can either accept the offer or reject the offer. Player 2 has only two strategies at this node. And this is a sequential game. So first player 1 makes an offer, and then player 2 observes this offer, and then he uh, executes his action, all right, or plays his action. So at this node, if x is the offer and he accept this offer, so player 1 will get 12 minus x and player 2 will get x. And if he rejects the offer, then both get nothing. Okay? So this is the game tree. You can take a minute and find the solution of this problem. The subgame perfect Nash equilibrium of this game. It may seem that player 2 has only two strategies, accept or reject. But if you think carefully, for each action of player 1, player 2 can have a strategy, right? So player 2 can have an action for x is equals to 0. He can have an action for x is equals to 1, for x is equals to 2. So he has actually a set of actions. That is the strategy of player 2. So player 2 strategies will not be given by just accept or reject. It will be given by a combination of actions, actually 12 combination of actions, stating not 12, 13 maybe, because from 0 till 12 there are 13 values, stating what will be his action for each of the actions of player 1. All right, and player 1 also. So player 1 also has 13 actions from 0 to 12. So if I'm writing this for player 1, so he can have different actions 0 to 12, but the strategy of player 1 will have only one value, that will be x. So this is the strategy of player 1. For player 2, his actions can be either accept or reject, but it is the strategy of player 2 will be a combination of 12 actions, right? So it can be either for the first, so from x is equals to 0 till 6, accept all. So accept, and from 7 to 12, reject. There can be multiple other actions also. For any value of x, you just accept. So in that case, the strategy will be accept, 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 and so on. It can be other, their player 2 can have other strategies as well. Right? So you should remember how are we writing a strategy in this game. All right? So could you find the best response of player to given x? So given x, what should be the best response of player 2? Or on the other end of this question, you can ask what are the different strategies you should consider to find the subgame perfect Nash equilibrium of this game.
I think the SPNE will be x equal to 1 because player 1 will try to keep everything with himself. If he offers 0, then player 2 will reject because then both get 0. So he will offer as minimum as possible, which is x equal to 1.
Right. So x is equals to 1. So player 1 gets 1, and sorry, player 2 gets 1. Player 2 gets, so utility of player 2 is actually, but this is not how we write. Utility of player 2 is actually 1, and utility of player 1 is 11. So I'll just explain this for other present here. So you see player 2 can have different strategies. The first kind of strategy is accept all. So whatever player 1 gives, we can accept all. So in such case, player 1 is better off giving 0. So x is equals to 0. For such strategy where player 2 is thinking of accept all, player 1's best response is to give 0. But player 2 can have other strategies as well. Player 2 can have accept if x is equals to x is positive, accept when x is positive, and reject when x is equals to 0. So in such situations, the utility of player 1 will become 0 because this will be the outcome of the game, because player 2 is rejecting for any value, for the value of x is equals to 0. So for this value, there is a threat to the utility of player 1 that if player 2 rejects, my utility will go from 12 to 0. Therefore, he will not play 0. Player 1 will not play 0 because although he is getting 12 when player 2 is playing accept all, there is a chance that player 2 may play accept greater than 0 and reject x is equals to 0. So in that case, x is equals to 0 is not the best not the subgame perfect Nash equilibrium of this game. So player 1 will try to offer a bare minimum. So the bare minimum is x is equals to 1. So when player 1 offers x is equals to 1, in that case, this will become 11, 1. And in that case, player 2 will always accept the offer because he is better off accepting the offer than to reject the offer. Therefore, the subgame perfect Nash equilibrium of this game is player 1 is playing. So the strategy of player 1 is actually x is equals to 1, and the strategy of player 2 is accept all. You can say accept all, or maybe you can say accept when x is greater than 0 and reject x is equals to 0. So this is the subgame perfect Nash equilibrium of this game. And the outcome is utility of player 1 is getting 11 and utility of player 2 is 1. Okay. So you may see this is not a very fair division of the resources. So we'll proceed and see how fairness comes into play if we repeat this game again and again. So now suppose we have a double ultimatum game. In this game, there are again 12 biscuits. Again, player 1 is offering, making the first offer. So he can offer from 0 to 12 any value. Suppose x is the value he is offering, and player 2 can either accept, and if he accepts, then player 1 gets 12 minus x, and player 2 gets x. Now, if he rejects, then we are at a new game where player 2 again plays, and he can make an offer to player 1 again. So it can be again from 0 to 12, and we are saying that he is making an offer of y. So if he makes an offer of y, player 1 can either accept the offer or reject the offer. If player 1 accepts the offer, then he will get a utility of y, and player 2 gets a utility of 1 minus y. Otherwise, both gets 0. So can you find the subgame perfect Nash equilibrium of this game? So this is a two-stage game. So if you see, this is a two-stage game. This is the first stage, and this is the second stage. You can take a minute and try to find the subgame perfect Nash equilibrium of this game.
Is it x equal to 0, owing to which P2 will reject and the stage will come to the next one and then he will offer y equal to 1?
So your idea is player 1 will offer x is equals to 0 and player 2 will offer x is equals to y is equals to 1. In that case, the outcome of this game will be 1 comma it will be 1 comma 11. So you are thinking this is the outcome of the game, right? This is how you are thinking it through.
Yeah,
Am I
but then
correct?
again, even yes, that is what I was saying. But now I'm just thinking that player one will not want him to go to the reject side.
Right.
So he will offer something in A, which is so basically player one will offer an X so that P2 does not reject.
So you see, your idea over here for this game is correct because this is just the same game which we have discussed earlier. This is a sub game of this entire game. So over here, the best response of player 2 is to offer y is equals to 1. So the best response of player 2 for this stage is to offer y is equals to 1 because that is what we have seen in the previous game, and that is the same game over here. So this utility will become 1 comma 11. All right. So y is equals to 1. We know that. So we are going using backward induction, the idea of backward induction. Now we can just remove this part altogether. So what the game becomes is, you see, player 1 can offer from 0 to 12 any value. Suppose he is offering x, and if player 1 accepts the offer, he gets the value of, so player 1 gets a value of 12 minus x and player 2 gets x. And if he rejects the offer, this will be the utility. Player 1 will get 11 and player 1 will get 1 and player 2 will get 11. All right, because this game has reduced to this value or this outcome. All right, now what will player 1 think? Player 1 think, if I offer a value of 12, all the cookies to player 2, so this is where player 2 is making, I will get a utility of 0 and player 2 will get a utility of 12. If I offer, so this is when x is equals to 12. Now if I offer x is equals to 11, if I offer x is equals to 11, my utility will be 1 and player 2's utility will be 11. Now you see, in both the cases, the utility of player 2 is 11. All right, but you see, there is a threat. What is the threat? Player 2 might reject the offer and both of them will get 0. So in that case, the utility over here will not be 11, it will be 11 times the probability he is accepting plus the probability he is rejecting times 0. So this probability of 11, there is a threat. So player 2 can give a threat, and this is a credible threat. He will say, if you offer one cookie to me, if you offer one cookie to me, sorry, not one cookie. What I'm saying is, just a minute. When he is offering 11 cookies, then he is getting a utility of 1 and player 2 is getting a utility of 11. All right. And in this game also, he is getting a utility of 1 and he is getting a utility of 11. All right. So let me see what happens when x is equals to 10. Then I'll come back because I have got it into some confusion. So when x is equals to 10, player 1 is getting a utility of player 1 is getting a utility of 2 and player 2 is getting a utility of 10. In that case, player 2 will reject the offer and he will get 11 and player 1 will get 1. So this is how, if x is equals to 10. Now if x is equals to 11, then he will get a utility of 1 and the other one will get a utility of 11. So in this case, this offer of x is equals to 1 will be the best response of player 1, because if he offers anything less than 10 or less than equals to 10, he knows that player 2 can reject the offer and he can always get a utility of 11 in such cases. So this is not the best response of player 1. Now if he offers all the cookies to player 2, player 1 knows that he can increase his utility to 1. Therefore, offering x is equals to 1 is the best response of player 1. All right. So I hope the confusion, my confusion was clear. I hope your confusion, if I have made a confusion to you, is also clear. So the best response of player 1 is to play x is equals to 1. And the game ends in first stage also. Player 2 will think there's no use in going to play going to the second stage. Let us accept the offer, because if I just extend it to the next level also, the utility will be same. So the game ends in first stage only. And therefore, this is the utility of both the players. Player 1 get a utility of 1 and player 2 gets the utility of 11. Is this all right?
So what you're saying is x will be 1, owing to which player 1 will get 11, player 2 will get 1, and
Yes.
he will not reject, because if he rejects, then he will have to give y equal to 1, otherwise P1 can reject.
You
And
see,
anyway, he is getting y equal to 1 later on, so that's why.
right. So there's a time delay. So you see, we are not bringing the idea of discount factor in this game. In just the subsequent game to this game, we will see there's a discount factor. In that case, this
No,
1
no,
and
actually,
11
I
will,
understand. I'm not getting into discount factor. Let's
right,
say a player 2 takes it to the second stage without
right.
a discount factor. If player 2 offers 1 to P1,
Yes,
then player 2 is left with 11. So
yes.
wouldn't player 2 threaten at the second stage that I will always reject unless you give me 11, x equal
So
to
it
11?
doesn't matter, right? If the game goes to the second stage as well, the utility remains the same, 1, 11, right? So there is no threat here. The threat will come when we will see in the next game. So that is why I got confused. The threat is not here. The threat is in just the next game to this game. You see, if player 2 rejects the offer, the utility will be 1, 11. If he accepts the offer, then also the utility is 1, 11. Therefore,
No,
1,
it will be 11, 1. If
right?
player 2 accepts the offer in the before the second stage, then the utility will be 11, 1. Because P1
No.
will get 11 and P2 will get 1. And in the second stage, he can get, player 2 can get 11. So it will be 111.
No, you are getting confused. Just a minute. You see, in the first stage, he's offering X to player 2. So if player 2 accepts, player 2 will get the value of X. So in that case, if X is equals to 11, so I have written 1 over here, it will be 11. So if X is equals to 11, player 2 will get a utility of 11 and player 1 will get 1. So he's offering 11 cookies or biscuits to player 2. So take 11. So in that case, at the end of first stage, if player 2 accepts, the utility will be 1 comma 11. That is all right.
Yeah, I am saying X will be equal to 1, not equal to 11.
So let me do this again. All right. So you see, player 1 when makes an offer X, and if player 2 accepts, the offer, so this is 0 and this is 12. If player 2 accepts the offer, player 2 gets X, whereas player 1 gets 12 minus X. All right. So if X is equals to 11, this utility will be 1 comma 11. All right, this utility. Now if player 2 rejects the offer, player 2 is making an offer to player 1 that take Y number of cookies. All right. And if player 1 accepts the offer, player 1 gets Y and player 2 gets 1 minus 12 minus Y. Right. And if he rejects, both get 0 comma 0. Right. So if in the first stage player 2 rejects the offer, there are 12 cookies. Player 2 can say, I'll offer you one cookie. I am offering you one cookie. Do you accept? And you see, one cookie is better than 0 cookies. One cookie is better than 0 cookies. Therefore, in this stage, player 1 will accept the offer and the utility will be 1 comma 11. So in both the cases, it is 1 comma 11. Is this all right?
Yes, okay, I understood.
Understood? So this is the first
Yeah.
stage and this is the second stage. Now, the thing I was talking about, the threat will come when we have a discount factor, and we'll see this in the next problem. So this is also a double ultimatum game with diminishing return. So in this problem, the game is same, but there is a discount factor going on. So suppose what is happening is, suppose there is a mother who is offering 12 cookies to her two child, and the rules of the game are similar, but whenever the first stage ends and if there is no agreement between the two, the mother is saying, I'll punish you both and take 2 cookies from the total. So that is how the discount is coming. So from 12 cookies in the next stage, the total becomes 10. All right. So initially they started with 12 cookies. If there is a disagreement in the first stage, 2 biscuits are lost. When 2 biscuits are lost in the second stage, there are only 10 biscuits remaining. And from then 10 biscuits, they have to divide. So this is how the diminishing return comes into play. And from this, we will move on and build more concepts in this today's lecture. All right. So you see, the same game I'm drawing again. Player 1 is moving. He can either give 0 cookie or 12 cookie offer. So this is X. The offer is X. Player 2 can either accept the offer. In that case, player 1 will get 12 minus X and player 2 will get X. If he rejects the offer, he can make a counter offer. So player 2 will play again. So the counter offer will have 0 to 10 because 2 cookies are lost. And he can make an offer Y. Sorry. Now, player 1 will either accept the offer or reject the offer. So player 1, if he accepts the offer, he will get a utility of Y. And if and player 2 will get a utility of 10 minus Y. And if he rejects the offer, both will get a utility of 0, 0. Now, whatever I have discussed in the previous problem, you take that idea and solve for X and Y. What is the value of X and Y? Okay. Just try and then we'll discuss. to proceed with the second stage first. Then we'll go to the first stage, the rule of backward induction. So this is the first stage. This is the second stage. Any idea how to proceed with this game? You see, the second stage game is very similar to the single stage ultimatum game. Over here, any value of y which is positive, that will make player 1 to accept the offer, because if he rejects, he will get a utility of 0. So any value of y which is positive, not 0, player 1 will accept the offer. Therefore, player 2 will offer the bare minimum, which is 11. That is what player 2 will offer. So y is equals to 1. What will be the utility of both the players? Player 1 will get a utility of 1 and player 2 will get a utility of 9. Is this all right? Now you see, is this all right? Now you see, we can remove this game. If you think about removing this game, then you see what will be the game now. This is 0, this is 12, this is x. Now player 2 will play. He can either accept the offer or he can reject the offer. So if he rejects the offer, then the utility will become 1, 9. Otherwise, the utility is 12 minus x, x. Now, you may be tempted to think x is equals to 9 is a good offer. You see, when x is equals to 9, this utility will be 3, 9. And player 2's utility is not changing. It is 9 in both the cases, in the first case as well, in the second case as well. And player 1's utility is more when player 2 is accepting. So what player 2 might do is he might reject the offer. So the threat over here is, if you give me 9 cookies, I will reject the offer. My utility will not change. My utility will be 9. You see, over here also it is 9, over here also 9. But I can reduce your utility. Therefore, x is equals to 9 is not a subgame perfect Nash equilibrium, because player 2 might threaten player 1 that I may reject the offer. Therefore, x is equals to 10. When x is equals to 10, the utility will become 2, 10, and player 2 doesn't have an incentive to reject. If he rejects, he get a utility of 9, whereas if he accepts, he get a utility of 10. Therefore, x is equals to 10 in this case is the subgame perfect Nash equilibrium. X is equals to 11 is also fine. You see, when x is equals to 11, the utility is 1, 11. Player 2 will not reject this offer. Player 2 will accept this offer. But player 1 can improve his utility by deviating. What is the deviation? Change x is equals to 11 to x is equals to 10. In that case, player 1 will not play x is equals to 11 or x is equals to 12 for that matter. He will play x is equals to 10. Therefore, x is equals to 10 and y is equals to 1. This is the subgame perfect Nash equilibrium of this game. All right. So you see, this diminishing return, delta, discounting of utilities plays a major role. Earlier, The utility. So what is the utility over here? This is the utility both the players is getting. Player 1 is getting a utility of 2 and player 2 is getting a utility of 10. Previously, when this discount was not there, player 1 was getting a utility of 1 and player 2 was getting a utility of 11. Therefore, some fairness is coming into play. Due to this discounting, player 1 could improve his utility from 1 to 2. And one more thing to notice is that this game will not proceed to second stage. It will end in first stage. Because what this offer, whenever player 1 makes this offer, player 2 will always accept this offer. And therefore, this game will not proceed to the second stage. These two things. Discounting improves the utility of player 1. Therefore, some kind of fairness is coming into play. This idea, and the second idea is the game is not proceeding into the second stage. Although the second stage is playing a major role. Due to the second stage, player 1 could offer 10 and get a utility of utility of 2. So second stage, that is important for the game. Although second stage is important for the game ends in the first stage. So these two are the main key ideas for this problem. Is this all right?
Yes, I understood, and it's very interesting. You made the first statement that player 1 improves his utility in case there is a discount if it is going to the second stage.
Yes, because
But
of
in the
this
lectures, I understood. But in the lectures, when they were talking about a continuous variable, where he gives x equal to 0 in the single stage, and in the second stage, he says x equal to delta 2, in which case his utility would be reducing from 12 to 12 minus delta 2. So is this statement valid for discrete but not for continuous? Is my understanding right or no? Am I
no, no,
wrong?
no. Over here, we are comparing a game where the discount factor is not there with a game where the discount factor is there. So two games where when we are comparing, in the first game we have not considered discount, and in the second game we are considering discount. We are comparing these two games. In the lecture, I guess these two games are not compared. Something else has been compared, right?
Yeah, lecture is a continuous variable. There it is not a discrete variable. So there they are comparing single stage and double stage, but with continuous variable. In
No,
continuous variable,
over
you don't
here.
get x equal to 1 single stage.
So again, there is some confusion in your head. You see, over here we are not comparing the game with single stage game and two stage game. We are not comparing that. We are not comparing a game with
We
one
did that.
stage.
No? 111 in the single stage, it was 111, and
No,
now it is 210.
no,
We
no,
compared
no,
the two
no,
of
no.
them.
In the single stage, this is the single stage game. In the single stage game, uh, player one
Acha,
is offering
11,
one,
1. Okay, okay,
and
okay.
he is getting one. So the utility is coming out to be 1, comma 11. Sorry, 11, comma 1.
Yeah, yeah. Single stage is 11, 1.
Yes, single
Okay.
stage is
So
11,
with
1.
discount and without discount, you're saying with
With
discount
discount
is
and without
210.
discount, right?
Understood. Understood. Okay, okay. Fine, fine. Yeah, clear. Clear.
All right. So the comparison is between different games. For this, it is with discount and without discount, and for that case, we are comparing it with single stage and multiple stages
Yeah,
or two
understood.
stage.
Yeah, right, right.
Okay. So now we are playing the same game, but there is no end. So what does I mean when there is no end? Because this is a finite. The biscuits are finite. So when the biscuit becomes 0, then the game ends. So the game is played until and unless. So the number of stages will be determined by the number of biscuits left at the end of the stage, and the last stage will be determined when there are only 2 biscuits, and if the whichever player's turn is, if he rejects, then 2 biscuits will be withdrawn or lost. Therefore, that will be the end of the game. Okay. So how many stages we will have? We'll have in the first stage 12 biscuits, in the second stage 10, third stage 8, fourth stage 6, fifth stage there will be 4, sixth stage there will be 2, and at the seventh stage there will be 0. Okay? But the seventh, so will not go to the seventh stage. Sixth stage will be the last stage. If someone rejects in the sixth stage, the game ends, right? Is this correct? First stage starts with
Okay,
12
because 2,
biscuits.
2, 2, 2 are reducing. Fine.
Yes, first stage starts with 12 biscuits. second stage with 10 biscuits, and so on. Sixth stage starts with 2 biscuits, and if someone rejects, then the game ends actually, because there are no more biscuits to be considered for 7th stage. All right. So there will be 6 stage for this game. Now again the question is, find the subgame perfect Nash equilibrium of this game. And this is a very interesting game. We will again have to apply backward induction and start from the last stage. All right. So let us name the players. Maybe that will be better. Player 1 is player A and player 2 is player B. All right. So over here, player A is making an offer. Over here, player B is making an offer. Again A, again B, again A, and again B. You see, if you're having any doubt, you can ask me. You see, in the first stage, player 1 is making an offer. Player 2 can either reject it or accept it. In the second stage, player 2 is making the offer. Therefore, I have written B over here in case of second stage. And again, if player 1 or player 1 means A rejects the offer in second stage, then player A gets to make an offer in the third stage, and so on. So A, B, A, B, A, B. So in the last stage, B will make an offer. Suppose it is X. So it will be 0 and 2. And player A, because I'm writing player 1 as player A, because stages and this player 1, player 2 might get a little bit confusing. So I'm writing A and B. So if he accepts the offer, they'll get a utility of, so he's accepting the offer. So he'll get a utility of X, and player 2 will get a utility of 2 minus X. And if he rejects the offer, both will get 0, 0. This is all right?
Yes.
Now for this game, so we are doing backward induction. So for the 6th stage, this is the 6th stage. All right. So for the 6th stage, what do you think is the value of X?
1.
1. Why? Why 1?
Same logic which was the single stage one logic. Because if he offers 0, he will player A will reject and both will get 0, 0.
Yes, player A might reject and both might get 0, 0. And if player 2 offers 2, then what is the issue? If X is equals to 2, then what is the issue?
Oh, so you are saying he will threaten that if you don't offer 2, I will reject. So I will not accept 1 also. Is that what you're saying?
So again, there are 3
So he can
cases.
do 2 offers, X equal to 0, X equal to 1, X equal to 2. Correct. Let's see all 3. Yeah.
So I'm asking, so this will not occur because there is a threat. Player A might reject it, because in this case also he is getting 0. In this case also he is getting 0.
Correct.
So this is not, X is equals to 0 will not be in the subgame perfect Nash equilibrium. I'm asking what happens when X is equals to 2. When X is equals to 2, the utility will become 2, 0. So you see player B is getting 0. Whereas if X is equals to 1, the utility will be 1, 1. Therefore, player 2 can deviate and improve its utility simultaneously. Therefore, player 2 will not play X is equals to 2. Player 2, or over here, player B will play X is equals to 1. Is this all right? So there is an incentive to deviate for player B from X is equals to 2 to X is equals to 1. Therefore, X is equals to 2 will be the, for this subgame, will be the subgame perfect Nash equilibrium. X is equals to 2 and player A is accepting. Is that all right? So for this subgame, X is equals to 2. So player B's action is play 2 and player A's action is accept.
So you're saying X equal to 2 or X equal to 1?
Sorry. X is equals to, yeah. Thank you. X is equals to 1.
But tell me, if A can also say that unless you offer me, even if you offer me 1, I will reject. But then he is also going to deteriorate.
That is not a credible threat.
That is not a
credible threat. Player B knows that if I offer him 1, he will have an incentive to accept. He will not reject it.
Understood. Okay. Yeah. So 1,
Right.
1. Yeah.
So this is for the 6th stage. Again, we will go back to the 5th stage. In 5th stage, A will play first. And in the 5th stage, you see how many cookies are there? There are 4 cookies. So there will be 4, 0, This will be again I'll writing y. Doesn't matter, I can write x also. So player B will play over here or player 2, doesn't matter. He can either accept the offer or reject the offer. Alright, if he accepts the offer, player 2 will get y and player 1 will get 4 minus y. And if he rejects, then he will get 1 comma 1, not 0 comma 0 by the way. Because if he rejects, then player B can make another offer. And what is the utility? It is 1 comma 1. Alright, not 0 comma 0. Right?
Yeah, yeah.
So over here, what is the value of y then? For this subgame, what is the value of y such that it is a subgame perfect Nash equilibrium? So how many value of y we can have? We can have 0, 1,
Y
2,
equal to
3,
1 or 2.
3, 4, right? 5 values y can take. So what do you think the value of y will be for this game such that it is a subgame perfect Nash equilibrium? You see, if y is 0, then the utility of both the players, I'm writing it over here, 4 comma 0. Y is 1, then the utility is 3 comma 1. For this it is 2 comma 2. For this it is 1 comma 3. And for this it is 0 comma 4, right? Now you see, player B can reject and get a least utility of 1. Therefore, he will not accept this because he is getting a utility of 0. Why would he accept this? Moreover, for this game, for this case, when y is equals to 1, there is a threat to player A. If player B rejects, his utility will go down from 3 to 1. Therefore, player A will not play y is equals to 1. Because if he does that, then player B can reject and he has no incentive to either reject or he's immaterial. He can either accept or reject. So to make a threat, there is a threat that player B can reject the offer and his utility will go from 3 to 1. Therefore, player A will not play this game. Now, for this, y is equals to 2, you see, 2 comma 2. The utility of player 2 is increasing, therefore, player B or player 2 will accept this offer. Alright. For this game, player 1 or player A will not make this offer because his utility is 1. Instead of that, he can get a utility of 2. Therefore, he has an incentive to deviate from this game to this game. Therefore, y is equals to 2 will become, for this game, y is equals to 2 will make this game a subgame perfect Nash equilibrium. Alright.
Yes, all right.
So this will be 2 comma 2. Now we can go to the fourth stage. Fourth stage, we will play and the cookies are 6 comma 0 and we have used x, y, let it be z over here. Now A will again have an, either he can accept the offer or reject the offer. If he rejects, this will be the utility 2 comma 2 because this will not be played. You see, when he offers y is equals to 2, he knows that this will not be played and 1 comma 1 will not be the utility. The utility will be this because this is only the Nash equilibrium outcome. So this will come over here and if he accepts the offer, player 1 will get z and player B will get 6 comma z. Is that all right?
Yes.
This is not there, sorry. So now tell me what will be the value of z.
Z equal to 3.
Right, z is equals to 3. Now for the, so again I'll just write it short. So z is equals to 3 by the same logic. If you go, z will be equals to 3. So we have done fourth stage. For the third stage, what will be the value of, again let it be x. What should be the value of x there? Offer A makes. What will be the offer A makes? If you don't see the logic, then we can draw the tree. If you see the logic, then we don't have to draw the tree. You see the logic? You
So
see,
here the payoff is 3, 3. So he will make 1 more than 3. So he will make 4, right?
I'm giving you the logic now. You see, there were 6 cookies. It was divided as 3 comma 3. When there were 4 cookies, it was divided 2 comma 2. When there was 2 cookies, it was divided 1 comma 1. So when there will be 8 cookies, 8 cookies, it will be divided 4, 4. So player A will make an offer of 4. The second stage, I'll just write x dashed and y dashed so that there is no confusion. So how many cookies are there in the second stage? There are 10 cookies.
Okay, 5.
So
Okay.
it will be 5. And in the first stage, I'll write z dashed such that there is no confusion. So there are 12 cookies and will be 6, so z will be 6. So in the first stage itself, player A will make an offer of 0 and 12. Player A, so this is z dash. Player A makes an offer of z dash is equals to 6, and player B accepts this offer. So this game, where there were 6 stages, this also ends in the first stage with a fair division of resources 6, 6. So do you see how fairness comes into play? So it is coming due to discount factor. So each time there is a delay, they both are penalized, and that is why they don't want to. So a game today is more beneficial than a game tomorrow. Not gain. Sorry. So the game ends in the first stage itself, but this doesn't mean that other stages are not playing a role. You see, if this was a only single stage game, the outcome was, what was the outcome for a single stage game? The single stage game, the outcome was 11, 1 and not 6, 6. So the other stages are playing a role. So there is a role for other stages, but the game ends in the first stage because of such an offer. And this is the Nash equilibrium of the game. So the game starts, player 1 makes an offer of 6 cookies, player B accepts the offer, and the game ends. All right. So you can
Yeah, clear. I'm clear.
is that all right?
Yes, fine.
So we can proceed with Rubinstein bargaining. All right. So before that, let us discuss the ultimatum game with continuous values. So suppose, so how can you think about a ultimatum game with continuous bargaining? Ultimatum game. So you see, we can take one example. Suppose there is a buyer. So did sir explain this? I don't remember actually. There is a buyer and a seller. Is this discussion in the lecture? So I may skip this discussion. All right.
Sorry, what did you ask?
Nevertheless, all right, I'll just discuss it. So the context of an ultimatum game for continuous values. So suppose there is a buyer and a seller, and the cost of production for a seller is suppose C. All right. So seller makes a good at a price C, and he is willing to sell the good at a price C or more, because the price at which he is making the good is C, and he is willing to sell the good at C or more. And this buyer, suppose this buyer is more powerful. Suppose this is the government and this is some agency who is offering a service to the government. And this buyer has a willingness to pay, and he can pay a price of at most P, where P is greater than C, obviously. Then only the transaction will occur, otherwise the transaction will not occur. So the seller has a cost of production C and wants to sell the product or service at C or more, and the buyer wants to purchase this good at most P. Now for this game, this ultimatum game, we are assuming, I know it is a strong assumption, but we are assuming that this is common knowledge. This P value and C value is common knowledge. The seller knows what P is and the buyer knows what C is, and other way around also. All right. So the difference P minus C, this value is what will be divided between the seller and buyer. So any value, suppose Q is the value which is fixed, which is greater than C and less than P, that at that price the product is sold. So the buyer gets Q minus C, and sorry, not buyer, the seller gets a profit of Q minus C, and the buyer, he was willing to pay at most P, but he paid Q. So his utility is P minus Q. So both are trying to maximize this value. Seller is trying to maximize Q minus C and buyer is trying to maximize P minus Q. Is this all right?
Yes, understood.
So this range C to P, we are normalizing this. We are normalizing this range to 0 to 1. All right. So the range becomes 0 to 1. Whatever this value is, C and P, we are normalizing it to become 0, 1. And since buyer is more powerful here, so buyer is going to play first. All right. So I'll just write player 1 or buyer maybe. Buyer 1 is making an offer that I will pay X amount for this service, and this seller can either accept the offer or reject the offer. If he accepts the offer, he gets a value of X and buyer gets a value of 1 minus X. And if he rejects, then both gets 0. So if this range was not 0 to 1, we can just use another color and show you. If the range was C to P and buyer is making a quote of Q, then seller is getting a value of Q because at that price the service is being purchased, and buyer is getting a utility of P minus Q. All right. And we are assuming C to be 0. If C is not 0, then it will be Q minus C. Doesn't matter. So it is normalized between 0 and 1. And this is how the game is written. All right. So this is the context of ultimatum game. Is it all right? Did sir give this context in the lectures?
No, I think the discounting thing, what I have seen is, I have not seen this P minus Q one of I have seen 0 to 1, and then he offers as a continuous variable X more than 0. That is what I
Right.
had
So over
seen.
here, I am just giving you context y 0, 1, and
Yeah,
and it is, and this 0, 1 is not a restriction. All right. So you can put any value and normalize it to 0, 1. Now we'll discuss the ultimatum game. You see this value of X. So we'll not work with C, P, and Q right now. So I'll just erase it for such that there is no confusion. Now you see this ultimatum game, buyer will always try to minimize this value of X. And he can do this using limit. So suppose what he is doing, instead of X, he is paying limit X where X tends to 0. And what will this become? 1 minus limit X where X tends to 0, comma, limit X where X tends to 0. So you see, in the limit, although this value is 0, seller is always better off accepting because limit X tends to 0, limit X tends to 0 will be better than 0, right? So in this game, seller will accept when buyer offers limit X where X tends to 0. Is this all right? Because that is how we will maximize his utility. Now, limit X tends to 0. This will actually not exist. What value will you give? You can give 0.0000. You can go on and on and on, right? So this, instead of this, the subgame perfect Nash equilibrium of this game becomes X is equals to 0 and S accepts. All right. So
even
this
though
is
his
how the
profit will
subgame.
be 0.
Sorry.
Even though his profit is 0, because he is then selling at cost.
Right. So you see, that is where the discount factor will come into play. So if there is a discount factor, B cannot offer X. Sorry, X. I'm saying B cannot offer 0. There will be some value higher than 0, and in such cases, seller will make a profit. So this is a very simplified problem where the seller is not making any profit. But this is not how the game plays into real life, and that fairness idea comes into play, and then therefore the division becomes not exactly fair, but yeah, uh, seller doesn't have a 0 profit.
Okay.
Right now we will take this idea with a discount factor. All right, so I'll not use this slide. Okay, we can use this slide. Suppose I'm using buyer and seller, so I'll just, because I'm using A and B over here, so let me write A and B. So for the time being, we will just keep that idea aside, buyer and seller, and we'll proceed to just player A and player B. So player A is making an offer. It can be between 0 and 1. He is making an offer of any offer we can take X, and player B can either accept or reject. All right. So we are now considering two-stage game. All right. Not an infinite stage game. We are currently studying two-stage game. Now, if he accepts the offer, then he will get X, and A will get 1 minus X. All right. Now you see, when there is a discount, so suppose the discount is delta. I am not able to write delta properly, so it may seem like I'm writing S. So I'm sorry for that. All right. So bear with me with that. So this 1 will be multiplied with delta, and the maximum which is left is delta, right? 0 to delta. The range has become from 0 to 1 to 0 to delta, as the case was previously. In the previous case, we had 0 to 12 cookies in the first stage, which became 0 to 10. Now from 0 to 1, we are going to 0 to delta. Now
When
there
delta
will
is
be
less
some
than
offer.
1.
Yes. Delta is more than 0 and less than 1. All right. Now he will make an offer Y, and player A can either accept the offer. So I'll just write AC for accept, and or reject the offer. So if he accepts the offer, he get Y, and if he rejects the offer, he gets 0, 0, right? And player A gets Y, and player B gets 1 minus Y. So this is a
Delta minus
two-stage
y.
game. No, we are assuming the value is Y, which is between 0 and delta.
Yeah. So the utility will be y, comma, delta minus y.
Oh, yes. Thank you. Delta minus 1. All right. Now for this game, for the second stage, you see this is same as what we have discussed over here. Therefore, the offer will be 0. Y will be 0 because that is what we have discussed for single stage. Offering 0 is the subgame perfect Nash equilibrium. So the utility will be 0, delta, and Y is equals to delta. Now you see, you can just remove this game and you can make this a single stage game. This is A, 0, 1. He is making an offer of X, which is continuous. And then he can either accept the offer B, or he can reject the offer. If he accepts the offer, player 1 will get 1 minus X, and player 2 will get X. And if he rejects the offer, this is the utility 0, delta. Now you see, delta is the maximum value B is getting by rejecting. And you know delta is less than 1, right? What A can do is, A can offer a value of exactly delta. Now you may ask me a question. In the previous case, when we have a discrete case, we were saying we will make bare minimum positive value, bare minimum value, but you cannot make it in the continuous game. You cannot say delta plus some value, because in continuous game there is nothing delta plus. So we'll say in the limit is offering delta. All right. So this X will be exactly delta, and the utility of player 1 will be 1 minus delta, and the utility of player 2 will be delta. And since this limit of delta is approaching from positive value from one side, then this player B will always accept the offer and not reject it. Therefore, player A is getting 1 minus delta and player B is getting delta. So this is the subgame perfect Nash equilibrium for a two-stage game. And moreover, we are assuming this delta to be same for player 1 and player 2 when we'll discuss this problem. So for the time being, forget about that. Over here, this delta is discounting of player 2 because in the second stage, we are saying that player B has a value of 0 to delta. So this discount factor is for B and not A. So don't worry about that. So this is what will be the outcome of this game at subgame perfect Nash equilibrium. Is this all right? So player 1 will make an offer of delta, player B accepts, and player 1 gets 1 minus delta and player B gets delta. Yes, you were saying something.
No, I'm clear. This is understood. I was just saying there is a small typo you made while writing in that branch on the right hand side. You have written y equal to delta. I think it should not be equal to delta.
Yes,
When
y equals to
b,
y is equals to 0.
it should be just y because niche y is equal to 0.
Yeah, I'm saying for here y will be 0 and then this will be 0. Thank you. Thank you. Thank you. All right. So this is how the two-stage game occurs. Now, when we have an infinite horizon game and we have discounting, so for simplicity, we'll assume that discounting of discounting of A and B are same, which is delta. We'll not assume delta 1 and delta 2. You can do that. It will not change how we are discussing this problem. But for simplicity, we'll make that discounting of A and B are same. Although this might not be true in real life. Somebody can be more patient than the other. So, for example, we have a firm, very big firm in the market, so he can wait 3-4 more periods. But someone which is a new entrant, suppose a startup, he might not be able to wait for long. So his patience is less than the patience of the other firm. In that case, delta 1 and delta 2 will have huge difference. Right? So for assumption, we are assuming by the way, in the discussion which problem professor has done, he has taken delta 1 and delta 2. But for our discussion, we will take it as delta. All right. So now we'll do this for infinite horizon game. Now, do you want to do it yourself or should we discuss how we are discussing right now?
So we are okay. We can continue this.
Right. So you see, when we have an infinite horizon game, we cannot
You can go to the next slide, no? Because there will be more space. Yeah.
Yes, I'll just go to the next slide. I'm saying that when we have a infinite horizon game, we cannot use the idea of backward induction. You see, till now, how did we solve the problem? We went to the last stage. We went to the last stage and then moved one stage above. And then when we ultimately came to the first stage, we got the solution of the game. So that is how backward induction works. But for an infinite horizon game, we cannot go to the last stage because we don't know a last stage. All right, so we'll use some other concepts to solve this problem. Now there is uh, one more thing to think about. You see, why infinite horizon? So does this type of thing play into real life? So could you answer why are we talking about infinite horizon? Because in real life we cannot have infinite horizon games. So why is this? Why are we studying this? Where can we relate this infinite horizon game in real life?
I don't know whether A makes an offer and B accepts or rejects. Or like, let's say if I go to a sabji wala, I go today, then I go tomorrow. No, that doesn't work because
In real life, infinity means you cannot comprehend infinity, right? So this assumption in this game, it will go for infinite horizon, is a very strong assumption. All right. So in real life, things do not go to infinity, right? If it goes to infinity, it will be very yeah. So in real life, we do not encounter infinite horizon games. So why are we? How is this so important? So you see, you can think this in other way also. So one way to think about this game is that this game is played for infinite horizon. But the other way you can think this game is that there is some probability that the game will end in this stage, and with some other probability, the game will move to the next stage. So both the players doesn't know if this is the end of the game or not. The game might go on to the next stage with some probability. When they are in the next stage, There is some probability that the game will end in that stage, and then some probability the game may continue. So in that case, this game will help us study those cases as well, when there is some probability that the game moves on to the next stage. And therefore, there is a positive probability that the game ends, goes to infinite horizon. All right. I will not say positive probability. It is non-negative probability. All right. So was that idea clear?
Yeah, clear.
Now we'll see how to think about this problem. You see, before we move on to solve this problem, you have to make some things clear. You see, when we had discussed this game, we were saying that there is stage 1, stage 2, stage 3, stage 4, stage 5, and so on. So we can divide this stage into odd and even. All right. So we can have odd stage, even stage, odd stage, even stage, and so on. Right. And now, since this is the infinite horizon game, you can think about that people might not able to distinguish between one even horizon game and other even horizon game. So in the odd period, A is making an offer. So over here, A is making an offer. In the even stage, B is making an offer. All right. So A, B alternate. So suppose you have come out from outside, you are an outsider, and you came and saw that A is making an offer. You will not be able to tell what is the period. You will only know that it is an odd period. Similarly, when you came from outside and you saw B is making an offer, all you will know is this is an even period. You will not be able to tell what is the which period it is. So it is indistinguishable between two even periods or two odd periods. So this is so this is not an assumption. You see, this actually plays into play. So what you understood this idea, right? So you cannot distinguish between two even periods or two odd periods. Therefore, the player will not actually make different actions. They will not take different actions in two different event stages. So player B might not take a different action at this event stage and a different action at this event stage, because it is actually immaterial. It is actually the same game occurring at each event period. And for player A, it is the same game occurring at same odd period, each odd period. Therefore, a strategy for a player at a stage will be same as that at the next subsequent stages. So player B strategy over here and player B strategy over here will be same. And this property is known as stationary property. All right. This idea of stationary property is clear? Or
Yes,
stationary
clear.
strategy?
Basically, what you're saying is
Right.
the action of a player, whether it is game n or n plus 2 or n plus 4, will be the
Doesn't matter.
same.
Yes.
Yeah. But
All
the
right.
payoff may be from 0 to delta or 0 to delta square or 0
Yes.
to whatever. So
Yes.
that is the only
Yes.
thing that may change, but the action will be the same, is what you're
Yes.
saying.
Their
Understood.
equilibrium action. Their equilibrium action. They might change the action. So they might go from accept to reject, but at equilibrium, their action will be same at each even stage or each odd stage.
Understood.
Right? So with this assumption, we'll begin. So I'll just write one more odd and even. This is A and this is B. So we will make an assumption, not assumption. Yeah, we will make an assumption. Suppose at this stage, whatever this stage is, but this is an even stage, B is getting a utility of VB. So somehow we have solved the problem for infinite stage. Somehow, we don't know how. We will say the utility which B gets is VB. All right. So we'll have an even stage, an odd stage, and again an even stage. So over here, B is making an offer. So when B makes an offer, so whatever offer B makes, A will get that utility. And whatever offer A makes, B will get that utility. All right. So this is the utility function I'll write in this table. All right. And here I'm saying offer is made by. So suppose in the even stage, we have calculated that the subgame perfect Nash equilibrium, at subgame perfect Nash equilibrium, the utility player B is getting is VB. So whatever offer she is making, it doesn't matter. The utility player B is getting is VB. All right, in the even stage, at any even stage. Now, when we are at this stage, our utility will be delta times VB, right? Because it will be multiplied with a discount factor. So here it was delta. So when you are at this stage, you will see it as delta times VB.
Okay.
Is that all right? And you see, whatever is this utility, that will be the offer made at this stage. So B's utility is delta. What offer will A make? He will make the same offer, delta, right?
Yeah.
Is that right? So A will make an offer of delta times VB. So B will get delta times VB and A will get 1 minus delta VB. Is that all right?
Okay.
Now, B at this even stage, we will see that A's utility is 1 minus delta VB. So I have to make an offer exactly equal to 1 minus delta VB, right? So what will B see at this stage? That A is getting a utility in the next stage, which is equals to 1 minus delta VB. So B will have to make an offer, which is delta times this value. So she will make delta times 1 minus delta VB. Because it is discounting, if you ignore that discount, it is 1 minus delta VB. And since we have moved to one stage, therefore we'll multiply our discount factor delta. So this is the offer B makes, delta times 1 minus delta VB. Is that all right?
Yes, understood.
So B will get a utility of 1 minus, this is 1 minus delta times 1 minus delta VB. Is that all right?
Yeah.
So you see, just we talked about stationary strategy. Since we are in an infinite horizon game, this utility and this utility will be exactly same and it will not change because this is an infinite horizon game and B will not be able to tell what is this and what is this because so this is about stationary strategy. There is another idea known as continuation value. It means that since we are in an infinite horizon game, the utility B is getting at even stage will exactly match the utility which he is getting at any even stage because this is an infinite horizon game. So this utility will be same. Therefore, 1 minus delta times 1 minus delta VB will be same as VB. And this is the same thing what sir has done in the lecture also. If you go back, you will see this is the same thing sir has done.
But it should be offset by delta. Na? Ideally, we are making an assumption
So
that
we
in the
have done
infinite
that.
game,
If you
we
see,
have
we
already
have
done
done
that
that.
by this delta test. But
Right,
why?
we have
How are
already
we
done
able
that.
to equate it?
So you see, when we are talking about VB, it is not about this stage. We are not saying it is for this even stage. We are saying that that VB is a value obtained for all subsequent. We have solved for all subsequent stages from this stage, and that
Yeah.
is that value which is the continuation value, and therefore this value and this value is same because that is the idea of this stationarity. If you stand at this even stage, we have obtained what is the complete value throughout. If you stand at this even stage or this even stage or this even stage, it doesn't matter. This VB will be same, right?
Okay.
You think about it. I think you are not very confident. Your OK was not very confident. This continuation value VB, what is this? We have obtained is it as if we are at even stage and we have obtained the utility of B for all subsequent stages. That is what VB is. That value which B obtains at an even stage considering all subsequent stages. So if B is in this stage or this stage or this stage, it doesn't matter because it is an infinite horizon game. You can add 2 more stages and 4 more stages or 6 more stages. It doesn't matter. So VB, considering what VB is, that is the key. It is that value which player B obtains standing at even stage. He doesn't know which stage it is, but that is the utility he'll get. And that is what we are interested in. That value is what we are interested in. We are assuming it to be VB and going to just 2 more stages. Because adding 2 more stages to an infinite stage game will not change the number of stages. Right?
Yeah. Okay. Okay.
So we are equating this and this because both are same due to continuation value. And when you solve this, I have just solved it. No matter, we can just solve it again. So it is 1 minus delta square VB is equals to VB. This will become 1 minus delta equals to VB times 1 minus delta square, and we can just do this. It will be 1 plus delta.
1
So
plus
VB
delta
is
square.
equal to, no, this will be plus.
Yeah, sorry, this will be plus and then this side will be.
So this is 1 plus delta. So VB is 1 plus delta. All right. So the utility of player B is 1 plus delta. Right?
Yeah, this so is anyway a discounting factor if you like finance the discounting factor 1 upon R.
Right.
Yeah,
So
okay.
you see, so I'll just, sorry, just change the color maybe. So over here, we have removed VB to 1 by 1 plus delta. Right. So at this stage, the utility of player B will be delta times 1 plus delta. Right.
Yes.
And at this stage, the utility of A will be, so we will just multiply delta and subtract it. You can just do it. I have done it. It will become delta by 1 plus delta. You can just do it again. All right. So you see, at an odd stage, A will make an offer of delta by 1 plus delta. At an even stage, B will make an offer of delta plus delta by 1 plus delta.
Sorry, can you repeat? At the odd stage?
At the odd stage, A is making an offer, right?
Yes.
So that offer will be delta by 1 plus delta. And that is the value B is getting, because that is the offer to B.
Okay. Okay.
So this is the offer A is making at an odd stage, and this is the offer B is making at an even stage. What is the offer? So offer for A is delta by 1 plus delta, and for offer for B is delta by 1 plus delta. Same offer. Why it is same? Because we have assumed delta 1 and delta 2. So delta 1 is equals to delta 2 is equals to delta. So that is why we have this simple equation. If we assume delta 1 and delta 2, so it will be a little bit complex. You can just go back and see the lectures. All right. So you see, at odd stages, A is making an offer of delta by 1 plus delta. At even stages, B is making an offer of delta by 1 plus delta. All right. So at any stage, the offer will be delta by 1 plus delta. Now, since this is an infinite horizon game, B knows that if A makes an offer, you see, so if A makes this offer delta by 1 plus delta at an odd stage, I'll just, over here I have written even, odd, even, right? So over here, he'll make delta by 1 plus delta. So when A makes this offer, B knows that at the next stage, I will get, am I trying to say? Achha, for before that, this is the subgame perfect Nash equilibrium of this game. Is that all right?
Yes.
Right. Now, when we have this subgame perfect Nash equilibrium, similar to the previous games, this game will not move on to infinity. At the first stage only, A will make that offer and B will accept that offer. That is what I was trying to do, and I got confused. But this is the idea. At the very first stage, A will make an offer of delta by 1 plus delta, and B will accept the offer, and therefore the game ends. Therefore, all the subsequent stages will not be played, even though the subsequent stages are playing a very important role in the game. So in the very first stage, A makes an offer of delta by 1 plus delta. So the utility of A will be 1 minus delta by 1 plus delta, and utility of B will be delta by 1 plus delta. All right. So this is the utility of A and this is the utility of B. And we know delta to be less than equals to, not less than equals to 1, strictly less than 1. Now if delta is strictly less than 1, take any value. Suppose it is 0.5. So if it is 0.5, you will have 1 by 1 by 2 by 3 by 2, which will be 1 by 1/3, which is 2/3. And over here, it will be 1 by 2 and 3 by 2, which will be 1/3. So you see, A's utility is more than B's utility. So this is known as the first mover advantage. First mover advantage. Whoever plays the first will get a higher utility, and this is because of this delta being less than 1. Now, if this delta approaches 1, if this delta is exactly equals to 1, suppose for the time being we are saying that delta is 1, although it shouldn't be 1, for the time being it is, if it is 1, then you will have 1 by 1 by 2, which is half, and ub is equals to 1 by 1 by 2, which is half. Therefore, for no discount, both will get a utility of half. Therefore, you see, whoever is patient means, so if you have patient, delta will be high. So delta value is high. Whoever is patient, their utility will be more. And whoever is less patient, their utility will be low. Right?
So here A utility is higher than B when delta is equal to half, but on the top left hand side we have said both the delta upon 1 plus delta, that is in Nash equilibrium. So there it is the same. Why is that?
Sorry?
See, on this
Just
page on the top upper left half you have written the SPNE.
so this I have written offer of A, and this I have written offer of B. So
Okay, that is not
when
utility.
it is offer, so A makes an offer in odd period and B makes an offer in even period. So in the first stage itself, A makes that offer and B accepts it. Because we are saying that this utility, you see, delta plus 1 by delta is same as delta plus 1 by delta. So in subsequent stages, the utility, so similar to this case, you see, this utility becomes same as this utility, right? So we will not move to the next stage. Doesn't matter. Just accept the offer. So that is what becomes here. So whatever A offers, you just accept the offer, because if you delay, you will get the same utility. All right. So in the first stage itself, A makes the offer, B accepts it. Utility of A is this, utility of B is this. Now, the exact value of utility will depend upon the value of delta. If the delta value is high, so we have not done delta 1 and delta 2. So if you go back and see the lectures, you can just see if delta 1 is high, A will have a higher utility. So higher the value of delta, higher will be the utility for that player. All right.
Yeah.
Okay. And that is so over here, this is known as the first mover advantage. Whoever makes the offer will have a higher utility because we're assuming delta is less than 1. Now, all this is okay, but you see, when we are bargaining, this kind of bargaining, so it is very, it is actually, now when we are bargaining, suppose you gave the example of fruit vendor or suppose vegetable vendor. So this period is very quick. So in 1 minute there is 30 offers or 40 offers, right? So this delta value is actually near to 1. When this delta value is high, when the time period is very long, right? So in real life cases, the delta value is actually close to 1. Therefore, the offer becomes fair. You understood what I said, right? When this time is very low, when the offer is being made in successions, so when the time elapsed from one period to the other is very less, in such cases, this delta value is close to 1 because it doesn't matter if you wait for 10 more seconds. So that delta value is actually close to 1. And in such cases, the offer becomes fair. Both the parties get equal utility. So this first mover advantage is only there when there is subsequent time delay. For example, Apple released a laptop in 2020, MacBook laptops with M1 chips. And that time delay when the next period came, that is when other player made a similar product, was very high. And in that subsequent stages, um, Apple had a first mover advantage. They had a very huge profit because of that. So this first mover advantage is very important in such kind of scenarios. Although this is not a bargaining scenario which I have told you, but I'm giving you some idea how first mover advantage can be beneficial if the time delay from one stage to another is high. If the time delay is not very high, for example, in the case of fruit vendor, this delta value is close to 1. And in such cases, There is no first mover advantage. The utility is nearly the same.
Okay.
Right. Okay. So we don't have a lot of time, so I can just maybe skip this part. So this is a Stackelberg competition. I guess this was discussed in the lectures. You can just go back and see this is just a two-stage game where the first player plays first and the second player observes and plays next. The order quantity is the decision variable for the first player and the second player, and we are trying to maximize the profit. So this is not related to this week's lecture, but nevertheless I have taken this because this would aid the subsequent discussion. But for the time being, I'm just skipping this. Right? So this is again a Stackelberg game, but with incomplete information. Now we'll have an. I'll just draw a table maybe for clarity. You see, we had a simultaneous move game and we had a sequential move game. We had, so this is time. So how time is, so when is the players moving, simultaneously or sequentially? This is about knowledge. So here complete information, incomplete information. All right. So for some of the scenarios, we know the equilibrium concept. So when we have complete information and simultaneous move game, what is the equilibrium concept we have known, studied? Complete information and simultaneous move game.
Pure strategy Nash equilibrium.
It might not be just pure, you can have mixed strategies as well. So it is just Nash equilibrium, either pure strategy Nash equilibrium or mixed strategy.
Yeah, correct.
Right? So for sequential move game and complete information, what is the solution concept we have talked about?
Subgame perfect Nash.
Subgame perfect Nash equilibrium. For simultaneous move game and incomplete information, what is the solution concept we have talked about?
Bayesian Nash equilibrium.
Bayesian Nash equilibrium. For sequential move game and incomplete information, what will be the solution concept we'll talk about?
I don't know.
So in this week's lecture, that was discussed. Perfect Bayesian Nash equilibrium. All right, or perfect Bayesian perfect Nash equilibrium, doesn't matter. All right. So in this week's lecture, this was discussed, perfect Bayesian Nash equilibrium. So for sequential move game, this idea of this equilibrium concept comes into play, perfect Bayesian Nash equilibrium. All right.
Okay.
So over here, forget about this Stackelberg competition. So I had took that example to discuss it over here. So we have two firms, firm 1 and firm 2, and we are assuming that there is some incomplete information. Firm 2 doesn't know what is the type of firm 1. So firm 1 can be of two types. Firm 1, so should I draw here? For the time being, I'm drawing here. Firm 1 can be of two types. It can be of low marginal product or product cost, and so firm F1 and F1 dashed. It can be high marginal cost. Not written over here. It is high marginal cost. So it can be of two types, right? And firm 1 has two strategies. Either he can play 4 or 8, and over here also he can either play 4 or 8. When player 2 plays, he doesn't know if he is playing with firm 1 of low type or firm 1 of high type. So this kind of game we had studied when we were talking about Bayesian Nash equilibrium. But if you go back and check, that was a simultaneous move game. Both players were playing simultaneously. For this case, it is a sequential move game. Stackelberg competition is actually a sequential game where player 1 gives not order quantity, production quantity, and then player 2 decides what is the quantity he will produce. All right. So after they have come here, player 2 or firm 2 will play. Right. So I'll just draw the table game tree again. That's why I'm not drawing it very accurately over here. So this is how it will play. When they are here, they will exactly then player 2 will play. All right. Is all right?
Yeah, okay.
Is this all right? Right. So you see, since player 2, so you just think about it. Player 1 will exactly know what type he is because he is the internal insider. He knows if he has a low marginal cost of production or high marginal cost of production. But firm 2 will not know this because he is an outsider. So firm 2 will exactly not know if he is in this node or if he is in this node. Therefore, we can connect these two nodes, right? So when firm 1 has played 4, so 4 is the production quantity. So firm 1 is saying, I will produce 4 quantities. So firm 2 will just observe that firm 1 has played 4, but he will not know whether firm 1 of type 1 has played 4 or firm 1 of type 2 has played 4. Therefore, firm 1 firm 2 will not know if he is in this node or in this node. Similarly, firm 2 will not know if he is in this node or in this node, right?
Yeah, okay.
Right? So this over here becomes incomplete information and you can have some utilities. And what you can say is firm 1 and firm 2, sorry, not firm 2, firm 1 and firm 1 dash, it is decided by nature. Nature is the one who is saying what kind of firm 1 is. So यहाँ पे nature play कर रहा है. So he will either, you can just give a probability. You can say with probability P, firm 1 is of type 1 and with probability 1 minus P, firm 1 is of type 2. Alright, so that is how you can do it. So this you can draw it another style that will help understand this problem more nicely. So over here nature is there, you see nature is over here, and he can either give with probability P firm 1 with type 1 or firm 1 of type 2. Now firm 1 of type 1 can have two strategies, 4 and 8. So you can just say this is strategy 4, this is strategy 8, this is strategy 4 and this is strategy 8. Now firm 2 will play, you see, he cannot distinguish between this 4 and this 4. So we have drawn it in the same section, so you can just connect it. You can say firm 2 will not know if it is in this side or this side. Similarly, over here, firm 2 will not know if he is in this side or this side. So this is another representation for the same problem. All right, you can have utilities. Is this all right?
So the node over there is F2 on the left and the right.
Yes. So yes, this is firm 2. Over here, firm 2 please. All right. Now, when we talk about perfect Bayesian Nash equilibrium, stating just the strategy is not complete. You have to talk about beliefs. So what will firm 2 do? Firm 2 will say, I will play, suppose Q2 is either 4 or 8, so I will play 4, assuming that my belief is firm 1 is of type 1. So that assumption, firm 1 of type 1 with some probability mu. So what firm 2 will have? He will have a belief. He will say that I have a belief that firm 1 is of type this with some probability. So that belief you have to state, and then only you will write the complete solution of perfect Bayesian Nash equilibrium. So just writing the strategies will not be enough for perfect Bayesian Nash equilibrium. You will also have to specify what is the belief firm 2 has for firm 1, and therefore that will complete the whole solution of this problem. Is that all right?
So P is the probability that firm 1 is on the left hand side, that is 4 type. And 1 minus P is the firm 1 is on the right hand side, which is
Right.
8 type.
Right.
And
So,
how will F2 write its like in the sequential one, we used to write P into, that girl is indifferent to boy or interested in the boy in that battle of sexes.
no,
And then we used to have that.
that was when we were talking about mixed strategy Nash equilibrium. You have to differentiate between
No,
some
no, not
things.
mixed. Battle of sexes, not mixed.
Right, huh?
The girl
Yes,
is
yes.
two types.
Yes.
The girl is two types.
Right.
She's
So over
either
there,
interested or not interested, and then the payoffs when she's interested and they go together, and not interested the payoff. So there we could arrive at that utility ka formula. How
right. So
will it?
over there, they were playing simultaneously. So one player did not observe what the other player is playing, right? So I'll give you one example. So suppose instead of firm one or firm two, let us assume there is. So I am saying firm one is a student and firm two is a company. All right. And this strategy, so I'll use another color maybe. So suppose this strategy is school graduate or just school pass out, S pass out, and this is college pass out. Right? School pass out and college pass out. So now the concept I am talking about is known as actually signaling. Yes, signaling. So I'm talking about signaling. We will see what signaling and this is screening and signaling is. Now you see there can be students of two types. Either a student can be of high capacity or you can say high caliber, or a student could be of low caliber. So that is decided by nature. I don't know. But what the company will see, company can either see he has went to a school or school pass out, or he is a college pass out. That is all he will see. He will not be able to see if a student is of high caliber or a low caliber. That is okay. So whenever a student comes to the company, he will see that he is a college pass out. Now he has to decide whether he is a high caliber college pass out or a low caliber college pass out. Again, in the same flow, when some school pass out student comes, the company has to think through whether this is a low caliber school pass out or a high caliber school pass out, because a school pass out student may deceive the company in the terms of thinking that he's a high caliber student, such that he gets a higher utility, right? So this kind of games where this PN1 minus P, although it is known that 50% of the time we'll have a high caliber student and 50% of the time I'll have a low caliber student, we will not exactly know what is the percentage of the student who is a school pass out with a high caliber. So what I'm saying is, what is the probability that he is a high caliber student given he is a school pass out? We don't know that. We know this, that probability is a school pass out given he is a high caliber student. No, we don't know this as well. All right, so this kind of probabilities is not known. We only know what is the probability he's a high caliber student, probability he's a high caliber student, and probability he's a low caliber student. These kind of probabilities we don't know. What is the probability he's a high caliber student given he is a school pass out? What is the probability he's a school pass out given he is a high caliber student? So these kind of things are known as beliefs. What do you believe? So someone comes to you with a school pass out certificate. What is your belief that he's a high caliber student? That is the main idea of this kind of problems. And what will be your strategy in such cases?
Okay, yeah, we will maybe go
Right?
back to the original one.
So we will take simple problem. This is a very complex problem. To solve this, you have to understand this idea of beliefs and so on. I'll take a very simple problem where this nature is not there. All right, but beliefs concept will come. Suppose there is player one. He has three strategies: left, middle, and right. Right. So when he plays left, he gets a utility of 1 and player 2 gets a utility of 3. Sorry. And when he plays left, he gets player 2 gets to play, and player 2 will have U or D, so up or down. Again, when player 2 is here, he can have up or down. Now suppose player 2 cannot distinguish between these two. Cannot distinguish two. You can think of it as a simultaneous move game. So when player one doesn't play R, then it is a kind of simultaneous move game. So player two should have a belief. What is the probability that he is in this node, and what is the probability he is in this node? The player two should have a belief. What is the probability I am in this node, and then I will proceed. What is the probability I am in this node, and then I'll proceed. So these are beliefs of a player. right? So the utility is 2, 1, 0, 0, 0, 2, and 0, 1. You see, when player 1 plays R, player 2 doesn't have a chance to move. But if player 1 plays L, player 2 gets to move. So player 2 actually doesn't know if he will get to move or not, right? So if you think this as a simultaneous move game, player 1 and player 2 are moving simultaneously. So I'll just type player 2 over here. Player 2 might not be able to know that he will get to move or not. Therefore, he has to make a belief that suppose I was able to move and player 1 played L, my belief that I will be over here is mu. So with that probability, I will be over in this node. And with this probability, I will be in this node. Alright. So this is where beliefs come. Is that alright?
Yeah, okay, you are solving this problem which was there, the 2100, which was there initially, is it?
So I am talking about this problem because the concept of belief will become more clear.
Okay, so these values are just like some values.
Yes, these utilities are some value. I have just taken some value. Alright. Now you see what is the expected utility, because player 2 doesn't know if he is in this node or he is in this node. So with some probability he can be in this node, which is his belief. Player 1 doesn't have anything. He will just play either M, L or R. But player 2 will have some belief. I have some belief that I will be in this node. I have some belief I will be in this node. So the expected utility of player 2, if he plays U, will be 2 times mu, 2 times mu plus 0 times 1 minus mu. So this will be 2 times mu plus 0 times 1 minus mu. No, this is the utility of player 2, right? I'm sorry. So this is the utility of player 2. It should be 1 times mu plus 2 times 1 minus mu. This is mu plus 2 minus 2 mu, which is 2 minus mu. Alright. So
And we
expected
do not
utility,
take anything pertaining to the right one option because he's getting a
because
utility of 3 over there.
so you see, when we are talking about over here and here, over here he is not able to uh, move, right? So he is not able to play. So when we are saying we are at this node and when we are at this node, so this node, when player 1 plays, player 2 doesn't have to play anything. So if he plays U or D, doesn't matter. If at this node, player 2 can either play U or D, it doesn't matter, or D. It doesn't matter if he play U or D, he will get a utility of 3. In these two nodes, player 2 have to decide whether should I play U or D, right? Over here, if he plays U or D, his utility will be 3. But over here, he has to decide, should I play U or should I play D? Am I making sense? Should I take another example? I have more examples as well if this is.
So you are saying there he is not at all playing U or D because there is no option. And hence, when you write expected utility when
His
player 2 is playing
expected.
U, that option doesn't come into the. Is that why
So
you
you
are not
see,
writing the formula?
yes, yes. So when I'm saying over this, his utility will not change if he play U or D. But over here, his utility might change if he plays U or D, right? He is confused between if he is in this node or he is in this node. We are taking expected
Okay,
utility.
okay.
So for this case, when he is playing D, his expected utility will be 0 times mu, 0 times mu plus 1 minus mu times 1. So this will be 1 minus mu. Now, you see that this utility is always less than this utility. So expected utility of playing U is more than expected utility he is getting when playing D. Is that all right?
Yeah, okay.
And this is clear with the idea of dominant strategy. You see, playing U over here gives a utility of 1 and playing D over here gives a utility of 0. Therefore, he will not play D at all. Over here, the expected utility he's getting is 2, and over here, not expected utility, over here, the utility he's getting is 2, and over here, he's getting a utility of 1. So he'll not play D at all. So he'll always better off playing U. Is that all right?
Yes.
Right? Now, whatever the value of for whatever the value of mu doesn't matter, it belongs to 0 comma 1, is better off playing you. Is that all right? Now we have to see what will player 1 do. So player 1 knows that player 2 will play you, right? Player 1 knows that player 2 will play you. So we'll have to calculate the utility of player 1. Sorry, the utility of player 1 when he plays L and player 2 will play U, because he know player 2 will play U, he will not play D. In that case will be 2, right? Utility of player 1 when he plays M and other player plays U is actually M and he plays U is actually 0. And utility of 1 when he plays R and player 1 plays U will be 1. So player 1 is always better off playing L instead of R or M, right? Player 1 will always play L. Is that all right?
Yes.
Now you see, player 1 will always play L. So the strategy is L comma U. But this is not exactly complete. You have to define what the value of mu is. You cannot just say mu is it belongs to 0 comma 1, because player 1 is playing L. Therefore, it is certain that player 1 will play L. Therefore, the value of mu will be 1. And this complies with this value, which is mu between 0 and 1. Therefore, this is a subgame, Bayesian subgame perfect Nash equilibrium, whatever you say. Subgame, not subgame, perfect Bayesian Nash equilibrium. So what did I say? You see, this game where mu is coming out to be 1, this complies with the idea where mu belongs to 0 comma 1. Therefore, the belief of player 2 where he says mu can be any value between 0 comma 1 is consistent with the solution which we are getting at equilibrium. Therefore, his belief is correct. So this problem I had just taken to explain to you the idea of belief. What is belief? So whatever his belief is in this, he can take any value between 0 comma 1, but he has to take his belief. So he cannot take any value between 0 comma 1. I'm sorry, I just said he can take any value. He cannot take any value between 0 comma 1. He has to say that mu will be equal to 1, and that should be his belief. I will always be at this node L. I will not be at any other node. Right?
Yeah, okay.
So this is where beliefs come. Now I'll take a problem where this will be very easy to understand. All right. So I know this might have been confused you. So we will talk about this game where we are talking about screening game. So we can have two kind of games. Screening game. First is screening game. Second is, I just forgot the name. Name is right. I just told you, right? Screening game and signaling game. Yes.
Signaling it.
Can you just help me with the spelling? I'm very poor with spellings.
Signaling. SIGNALLING.
Signaling game. I'm sorry for that. Yeah. All right. So yeah. So we will talk about first signaling game. So in signaling game, the first mover is not uncertain. So the first mover, we can say the first mover is sure what he is playing, but the other mover, the uncertainty is in the type of other mover. The first mover is not, so there is no uncertainty in the first mover. The uncertainty is in the second mover. Okay. The first mover, there is no uncertainty. When he is there, he is only of one type. So first mover is only of one type, only one type. Second mover, there can be multiple types. In signaling game, it is the opposite. The first mover have multiple types. And second mover is of one type. Okay. So if you go back in this example, you see the first mover can be of two type, either low or high. Therefore, this was a signaling game. First, we will see what your screening game is, all right, and then we will move on to signaling game. So take the example of entrant, where he will enter and there is an incumbent who will either fight or accommodate. All right. So there can be two types of entrant. There can be two types of incumbent. So this was actually the discussion of previous week's lecture, when sir told you that there can be two type of incumbent. One can be aggressive type. He is willing to fight a lot. There can be another type of incumbent where he doesn't want to fight and he wants to don't want to fight. All right. So you see, when we have first mover, he is the entrant. He doesn't know if he is facing an incumbent which is a aggressive type or which is a non-aggressive type. So what we will do is we will name nature, and nature decides if player 2 is of aggressive type or non-aggressive type. So I'll just say strong or weak, which is better. So player 2 is weak. Over here player 2 is weak, and over here player 2 is strong. All right. So if he is strong, he will fight. So therefore player 1 doesn't know if he is in this node or this node. He can either enter the market or remain out. Enter the market or remain out. If he remains out, the utility player 1 will get is 0 and player 2 will get is 1. Again over here, if he remains out, he will get a utility of 0 and player 2 will get a utility of 1. But if he enters, the incumbent or player 2 can either fight or accommodate. So this is a weak player 2. If he fights, player 2 will get a utility of minus 0.1 and player 1 will get a utility of 0.7. So these are the values I have taken in my example. And if he accommodates, player 2 will get a value of 0 and player 1 will get a value of 1. All right. So these are consistent with the idea of the problem. Right. So over here also player 2 moves. He can either fight or accommodate. So if he fights, this is a strong opponent. So he will get a utility of 0.8 and player 1 will get a utility of minus 0.2. Right? And if he accommodates, he will get a utility of 1. Player 1 will get a utility of 1 and player 2 will get a utility of 0. So player 2 over here is strong and player 2 over here is weak. All right, is this clear? Strong and weak. So over here, the first mover is of one type, the second mover is of two type. And you see, this is a little bit different structure of the problem than the previous one. Is that all right?
Yeah.
Now, this problem we have solved previously. You don't have to bring in beliefs in this problem, but even if you bring in beliefs, the problem will be same, right? So suppose this is with probability P and this is 1 minus P, right? And without, I'm telling you, without even bringing beliefs, you can just solve this problem using the concept which we had discussed earlier. You see, we can use backward induction. If player 2 is of weak type, he will always try to, so player 2 will always try to accommodate. So I'll use another color. Player 2 will always try to accommodate, right? And if player 2 is of strong type, he will always try to fight, right?
Yeah.
Knowing this, what will player 1 do? Player 1 with probability P will encounter a weak opponent, and with probability 1 minus P, he will encounter a strong opponent. So he can get his expected utility of, you can just take that idea because I am short of time. You can just take this idea. So player 1, you can find the expected utility of, so what you have to do, expected utility of player 1 when he plays E. So what will it be? So you see, with probability P, he will encounter a weak opponent and his utility will be 1. And with 1 minus P, his utility will be, with utility 1, probability 1 minus P, his utility will be this. So this is the expected utility if he enters. Expected utility of player 1, if he remains out, you can just calculate and then you can just do the same thing which we have done. You can just take expected utility of 1 is greater than 2 and then you can just obtain. So you can just take this is greater than this and you will be able to obtain the value of P. And that is the belief of player 1. So if player 1 believes, so suppose I'll just do it quickly. So what will happen? Remain out, his utility will be probability 0 and he will get a utility of p times 0, and with probability 1 minus p he will get a utility of 0. So this is actually coming out to be 0. So if this value, whatever this is, greater than 0, so you will get a value of p. Suppose it is greater than equals to, suppose something 1/3. Suppose we are getting is 1/3. So what does this mean? If player 1 believes that player 2, being a strong opponent, is more than 1/3, then he should uh, enter. And if it is less than 1/3, then he should remain out. And that is how the screening games play. All right. So this is about screening game. So this is same as what we have discussed in the previous class. The game becomes interesting when it is a signaling game. We will just draw the same diagram. Nature can have, so it can have two, firm1 and firm1 dashed. Firm1 can play, so I'll just use my diagram. Yes, so firm1 can play either so firm1 can either play left or right. For the time being, I'm assuming right or left. Now firm2 can have two strategies at each node. All right. He can either play up or down, up or down, up or down, up or down. And the utilities are 0, 2, 2, 0, 1, 1, 3, 4, 4, 3, 0, 5, 5, 3, and 2, -1. All right. So with probability 0.5, firm1 is of type 1, and with probability 0.5, firm2 is of type 2. Right. Now you have to decide, and these two are indistinguishable, and these two are indistinguishable. Is that all right? Now firm2, this is firm2. Firm2 doesn't know if he is in this node or this node, so he has to make some beliefs. All right, so he can say I have a belief that with probability p I will encounter this node, and with probability 1 minus b I will encounter this node. All right, again with probability mu I will encounter this node, and with probability 1 minus mu I will encounter this node. So these are the probabilities for each of the nodes. Now there can be two kind of strategies. One is separating strategy and one is pooling strategy. In separating strategy, firm 1 will select different strategies. So firm 1 of type 1 will select L, R or R, L. In pooling strategy, both will select same. So either LL or RR. All right. So these are the four cases which can happen. And you know, firm 2 will only observe this, that firm 1 is playing either L or firm 1 is either playing R. He doesn't know which type of firm it is. But the strategy of firm 1 will be written in this tuple. You understand why, right? Because if firm 1 is of type 1, he will play the first action. If firm 1 of type 2, he will play the second action. Right? So this is how we wrote strategies. So if firm 1, in girl and boy also in that game, Battle of Sexes, we wrote two tuples. If girl is of type A, she will play this. If girl is of type B, she will play this. So this is the strategy of the firms. So strategy of the firm can be LR, RL, LL, or RR, right? Is it getting confusing?
Okay. So who is L1? Who is F1? Who is F2? I'm not clear in those four things. LR and RL. So first one is F1, F2, F1, F2, right? Is that
So
what
I'm
you're
saying, so this is F1, F1 dashed. It means firm 1 of type 1 is playing L, so for this case, and firm 1 of type 2 is playing R. That is what it means. So when you specify a strategy, if you go back and see for any
No, I know
sequential,
that. Couple I know. Here I'm not clear which one is LR is F1, F2, F1 dash, F2 dash, or it is what do you think is F1, F1 dash, F2, F2 dash.
these strategies are for firm 1 either or firm 1 dashed. There is no firm 2 right now. Firm 2 has up and down. It doesn't have right, left or right.
He had only left and right.
You see, firm 1 is of 2 times. So to specify the strategy of firm 1, you have to specify both the actions for each of the types. So when I am writing L comma R, I am saying firm 1 of type 1 will play L and firm 1 of type 2 will play R. This is the strategy of firm 1. This is the strategy of firm 1, right? So this is a combination of two strategies, two actions, because you have to specify a strategy action for each of the type of player. If you are having a confusion in this, sir has solved the same problem, same problem with a different.
Yeah, okay, though I will see in that video because I have not seen the lectures of this.
Okay, you have not seen the lecture, right? Then it will be yeah. Okay, okay. Just I'll give you
Okay,
one
so
brief.
F1 the two times, L and no, it's okay. I'll see the lecture. What you're saying is firm one is of two types, just like that girl was interested and uninterested. But
Yes.
there are two types. So firm is of two types, and within that, it is having two strategies, so two square, and hence four options. That's what you're saying.
So this is not the.
LRRL, LLR.
There can be four combinations, right? L, LR, RR,
And
RL.
then why you are just naming it, separating and pooling. And where is the
Yes,
funda of
yes.
signaling coming? What's the? I'm still not able to understand in terms of English, not the numbers. What is screening? What is signaling? Signaling, what
So
I thought is like levers and PNG are fighting. The levers know that PNG is going to enter with the shampoo, so levers will reduce the price. Or it
no,
will
no.
say that I'm putting up a huge capacity. That is signaling, is what I had understood. But this
I'll just
screening and signaling and separating pooling is what is.
right. So you see, these are strategies. We are dividing it into two groups. We are saying if the both the strategies are same, then we'll call it pooling kind of strategies. If both the strategies are different, we'll call it separating strategies. It is different
Okay,
from
that's clear.
signaling.
Yeah.
It is different from screening and signaling. In signaling game, so if I am a student and I am a hardworking student, I'll try to signal that thing to the recruiter. So I will try to signal it. So you see, if I go and directly tell him, ki, Bhaiya, I am a hardworking person, he will
Yeah, so
think
I'll
ki
show
he
my
is
projects, I will show my certificates, achievements,
right.
blah, blah, blah.
So
Yeah.
in some kind of way, I will signal. So that is signaling. In screening, it is from the view of recruiter. Recruiter doesn't know if I am a weak student or a strong student. He will try to do something. For this example, the the player one, who is the entrant, he will try to understand what is the type of the incumbent. So the interviewer will do some action such that
So
he
that
will
he
try
can
to
filter
screen.
the student, right?
Yes, yes, yes.
Okay.
So that is where signaling and screening comes into play. So I
Okay.
will end this lecture today. You can go back and see professor's lecture. This is the same problem I had taken, but I have just
Okay.
changed the utility values. All right.
Okay.
And
Actually,
this
in
is
the
the last.
exam, we are going to get 75 marks. So is it going to be 75 questions of 1 mark each, or how is it? Do you know? Are you aware? Or
No, so you see, we are TAs of this course. There is some tutor of this course. So these questions will be better answered by tutors. You can just post this question in the discussion forum and you will see some mail ID is of some other person. Those are tutors who are replying and not the TAs. So they will be better
okay.
able to
Okay.
tell you it is these queries will be solved by them.
Okay, thank you. Thanks a lot. It's good that these sessions were done. Otherwise, it wouldn't have been possible to follow only the video and understand because this also is a very complicated topic. But yeah, thank you.
Right. So I hope so you can just give feedback to the NPTEL
Yeah.
about the teaching. Yeah. Thank you.
Okay. Thanks. Thanks. Bye.